Welcome, everybody. My name is Andrew Jones. I am the Executive Director, Climate Interactive, and I am here with Ava De Leon and Catherine Markova, two team members here at Climate Interactive. And we're thrilled that you are here and on time for the En-ROADS Climate Workshop on the top 5 surprising insights that come out of global models and En-ROADS. As you get oriented, would you please open up another browser window? Ava, would you post the link to polev.com? If you're looking at the image, you all can see up here, top left, here's the link to go to in your other browser window, or here is the QR code. You can look at that to join this poll, because we want to know where you are. Oh, and you're doing it. We have people in the US. Seattle-ish, California, Utah, and someone on the East Coast, someone in China. What is that? Germany, Brazil. All right, you're doing it. So come and tell us where you are. We had a session this morning, 7 a.m. Eastern, and everybody was in a very different time zone, but it's great to see so many people on the East Coast of the US, the West Coast of the US, Canada, some in Europe where it's later. Let us know where you are. We're thrilled that you're here. If you have things to say to the others, write into chat if you would. We're going to be using chat a lot. And if you have questions, write into Q&A in Zoom. Write into Q&A in Zoom. We'll be so happy to see what questions you have and try to handle them, mostly at the end of the session. So as you're joining us, please open up another browser window. The link is there at the top of my screen, and maybe Ava, you could put it into the chat again, how you can get into the chat. We see people from a lot of places. I'm actually going to move to a second question. I'm curious if you have ever used or played with the software before today. Have you? Or seen it? Kind of curious how many people are brand new to En-ROADS. It's funny, we don't find that many people anymore in climate who are brand new to En-ROADS. It's really gotten around. We have 1 million users around the world now who in the 20 languages. So 88% so far have used or played with the software before. Great to see it. If you're just joining, my name is Andrew Jones. I am the co-founder and executive director of Climate Interactive. I'm here with Ava De Leon and Catherine Markova. If you have questions of us, go to Q&A, go into the chat to talk to each other, and here we go. Most of you have seen the simulator before. That means I can move a little deeper into the model. We're going to be talking about surprises. What are the top surprises that come out of playing with En-ROADS? This is where we are in X and LinkedIn. Go find us there if you want to write things about it. We're Climate Interactive. We're a not-for-profit think tank. We're really reacting to this challenge in the world. Top decision makers are being flooded with many low priority actions, but also so many possibilities of addressing climate change. How do they sort between high priority and low priority? Well, they need access to cutting edge tools like En-ROADS and the insights that come out of them. And they need access to people in their countries who can advise them and help them separate between what's needed and what's not quite as needed. We're doing all of this with our simulator, En-ROADS. Here it is. Ava, can you post a link to the simulator itself? It's available in 20 languages. It allows you to test things like, well, deforestation. What if we reduce deforestation? What happens? Not just what happens to the energy system, but what happens in the land system to deforestation and mature forest degradation. You can see very quickly what the results are, what it would mean for temperature, and for important impacts in the world, things that we care about, like the probability of an ice-free Arctic summer in any year. That's the simulator. It is here for you to use. It is also here for you to invite us to come and run a workshop for your colleagues, your bosses, your board of directors, your community. We can run workshops, and we have now 780 people who can run the workshops as well. Okay, let's dig into this really cool topic. This is a topic that is about systems thinking. Systems thinking invented, the field of systems thinking, of system dynamics modeling, invented at MIT Sloan School of Management in the 1950s. So it's taking a perspective of exploring the interrelated nature of the world. And we do continue to work with these folks at MIT and the system dynamics group there, and a group called the MIT Climate Pathways Project. John Sturman is one of the co-builders of the model. This is the model. And this is, I partly present this just to show how tightly coupled and driven by feedback processes this system that we're managing is. And each of us has a map like this in our head of what affects what. I just reduced deforestation, and when I did that, you might have thought, how does that play out in a system like this? Down over here, it's a policy and scenario, reduce deforestation. And so what's that going to do? That's going to change food and agriculture and land and forests, and then climate impacts. And then that feeds back to the population and many, many interrelationships. What I'm going to be doing today is to use the model to improve your understanding of the system by pointing out 5 different areas of surprises, things that you wouldn't think would happen in this tightly coupled, complex system, a system that is governing our future when it comes to the viability of our lives on Earth, the preservation of equity and justice on Earth, and our overall economies. So let's dig in. Here is the setup. Here are the 5 big surprises. I'm curious which ones you are the most interested in. So please vote. What interests you the most? The 9 ways to boost wind and solar growth. A test of sufficiency. Is the clean energy revolution enough to meet climate goals? The 5 least discussed carbon dioxide removal methods. You're voting and voting. Here we go. The interaction of carbon pricing and energy efficiency. They're thought of 2 very different policies. They're not. They're tightly coupled. What is still possible today? You're voting. This is great. So curious to see, what do you all think? Which of these are you most curious about? You want to invest in your systems thinking ability about what is possible today is vote number 1. I will make sure to get there. I will make sure to get there over time. By the way, if you have questions, go to Zoom Q&A. Write it in there, and Catherine and Ava will answer many of them, the questions. And many questions, we're going to wait until 60 minutes in. We're going to stay late and answer more of your questions verbally. Please use the chat as well. If you have serious questions that take a lot of time, we'll send you to the support page. Ava, can you post the link to the support page where the FAQs and all are? Okay, interest in all of it. I'm going to start with these 9 ways to boost wind and solar. Okay, we're going to do these tests of the 9 ways to boost wind and solar here in En-ROADS. And I want to just give you some of the basics of what is going on in the model. Here's the baseline future. This is not our forecast of where things are headed. We are not going to go here because we're going to take so much action to reduce temperature. But it is a good starting point for model experimentation that captures current policies around the world, like the fact that the world has about a $5 per ton carbon price. 20% of the world's emissions has a carbon price on it. And no, you have 25%, and the average is about 20 bucks. So that averages out to $5. All right. There are a lot of other improvements in the system that we just believe are coming. Global population is slowing. GDP per capita is growing pretty robustly. Efficiency, we call it the energy intensity of GDP, is falling steadily as we shift towards a service economy from manufacturing, and also technologies get better. Think of lighting going from incandescent to fluorescent to LED and on and on. Motors getting more efficient, and transportation systems, all of these things reducing energy intensity. Carbon intensity is, where do we get our energy? More wind and solar, less coal, less oil as part of the mix. So that carbon intensity coming down. This is all the baseline. And where do we get our energy? I was just showing you that. We're assuming coal is sticking around. We're assuming in the baseline, oil on top of it, in blue is natural gas. Then you see that growing wedge, that's wind and solar. And we're going to experiment with what would make that wedge grow more and more and more with the 9 ways that I'm telling you are out there. Bioenergy in pink, nuclear, and then on top of that, if we invent it, boom, we invented it, then you would see the top one of wind and of new zero carbon energy, like fusion, thorium fission, maybe advanced geothermal. That's on the top, but it's not in the baseline because it doesn't exist. Okay, how do we make this grow more? The wind and the solar. I want to show you first one of the assumptions behind it, why it is growing exponentially here in the 2020s in particular. It's being driven by a reinforcing feedback loop we call economies of scale. And in this, every doubling of cumulative installed capacity reduces the cost of wind and solar 20% by what's called the progress ratio. And in the model, you can experiment with if it's higher. It's not something you can really change. You can't choose to learn faster, really. It's not a policy, but it's important. It's shown here under assumptions. You see where I went? Simulation, assumptions, under assumptions, progress ratio. Renewables, here are the studies that say it is 0.8. That is 1 minus 0.8 is the 20% drop in every doubling of cumulative capacity. McDonald et al., Junginger et al., here are the studies. And when you see it's blue, you can always click on it and say, I want to go read that study. I don't believe it, or how did they come up with it? Here is the study itself. So you can go and look at it. And if it were higher, imagine if it was 30%, and every doubling gave us a 30% drop in cost, then boom, 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 it would be growing a little more. So the first answer is, what would make it grow more is if there were faster learning. If the reinforcing loop worked more strongly, we would see more wind and solar growth. Okay, that's number one, a stronger feedback loop there. The second, I'm going to ask you to come up with yourself. So what are the second, third, fourth, fifth, and on? Please go to the poll. And what else would boost growth rates for wind and solar? Click to the right or the left of the dot. Afforestation, someone says. Carbon pricing. Well, there's the simplest, right? Just subsidize renewables. But a lot of people are saying, hey, let's price carbon. Less coal. Energy efficiency, you put right on the dot. If you want me to move it, go to the right or left. Oh, to the right on energy efficiency. Electrification, more energy efficiency. Now, note the goal is, I'm giving you a unique test. What would boost growth rates for wind and solar? People are voting less fossil fuels, more carbon pricing, energy efficiency, less deforestation, methane, electrification, more economic growth, more population and economic growth. You're getting it. This is it. Fantastic. Keep voting. All right, I think I get your idea. Let's move and do it. Okay. Uh, some, well, just the basics of this. People, population, more assumptions. It's difficult to imagine policies to do this, but of course, if we had more people, there would be more energy demand and more desire for wind and solar. Of course, temperature just went up with more people. More economic growth, more energy demand, a lot more temperature. Why? Because we don't just get more renewables, we also get, in this case, a good bit more natural gas. And we get a lot more fossil fuels, more oil, etc. Okay, so those are just some of the basics. And it's being driven by growth in GDP, which is being driven by growth in population and GDP per capita. What else did you vote for? Well, the simplest, of course, is just set a subsidy. What if we subsidize? And I'm going to go to financial, and down here, the marginal cost of electricity production. A subsidy makes renewables even cheaper. 2000 to 2100. See that green line? Cost of wind and solar down, 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 down. Cheaper than coal in brown, cheaper than natural gas in blue, right here. A lot cheaper than nuclear up here in light blue. If we subsidize it, watch the green line. It goes down a little bit more. And if we subsidize it, it gets a little cheaper relative to the others. Boom, up go renewables. Absolutely. That's another way to boost growth is the subsidies we see all over the place. Right above my head are solar panels. And I've got a tax subsidy here in the United States when I put those in. Okay, boom. That's a good way to do it. I want to note, though, the second one, interesting, is sparked by something. If I increase it a little bit more and a little bit more, look at this. It gets cheap. But notice the 2040s, it's getting expensive again. What is going on? And can we do something to avoid it getting more expensive? Well, what is going on and what's slowing the growth? You notice it's growing faster and then more slowly in the 2040s? What is going on is that we're getting a large amount. Let me just see this. Got moving too fast. We're getting a large amount of our electricity from variable renewables. Wind and solar are variable. They work best, and you can use the electricity best when the sun is shining and the wind is blowing. How do we make sure that we have power, electricity, when that's not happening? Well, firm or non-variable renewables or power, such as nuclear, such as coal and gas, will really help deliver electricity to people. When we get a large percentage up here in the 2030s and 2040s, 50% electricity consumption from variable renewables, up here in 2040, 60%. At this point, what we need is more energy storage. And it's making things more expensive when we don't have that storage. So let's go look at storage. We do have hourly, daily, and seasonal storage, particularly growing in the 2040s. What if it were cheaper? So this is the second big area. If we, through technologies and through business models, are able to have cost reduction in other storage, battery, hydro, etc. Look at the gray area over on the top right. More seasonal storage, long-term storage, month-to-month storage. And when we boost it, you can see that we get more growth in wind and solar. Another opportunity that's a pretty exciting breakthroughs that may happen, we'll see, could be storage in using hydrogen. as a way to store some of this energy. We don't exactly know how that's going to play out. In the model, there are many assumptions and many kind of uncertainties that we may want to look at for another time. The role of demand response, the leakage rate, because hydrogen does leak and it messes with methane and therefore is an indirect warming agent. And there are other factors like the round trip efficiency of hydrogen storage, many other considerations. But the main point is here. The second big way is if we can continue to solve storage and variable electricity production problems, then we get more growth in wind and solar. Okay, that one was buried. None of you voted for it because, well, I didn't really show it. So it was hard to see. What else did you vote for? Well, besides directly promoting renewables, many of you voted for carbon pricing. If we make coal, oil, and gas relatively more expensive, we can see how that happens with carbon pricing, then we get more investment in wind and solar. So watch over on the right, marginal cost of electricity production. Here it comes. We're going to set a carbon price and watch coal, oil, and gas get more expensive. It goes up. And then wind and solar in green is relatively less expensive. We get more growth in wind and solar with the blue line on the left. We also could get it by saying, all right, directly discouraging or taxing coal or gas or even oil indirectly will lead to some small growth in wind and solar. That's the other way to get there. Okay, what else? What else did you have? Well, the next one is going to be about electrification. And down here, I think I have overall, let me see, I think it's electricity. Electric share of total buildings and industry equipment. That's this one right here. If we electrify buildings and industry, then we get more electrification of this. We'll look again and see of electric share of transport. If we electrify transport, then there'll be more demand for electricity, more electrified transport. This is vehicles, this is charging infrastructure. You can see many of the assumptions for what we're changing underneath here. More growth in wind and solar. These are two things that would boost renewables a lot. So that would be another growth for it. All right. Next one that you suggested was energy efficiency. Energy efficiency. So somebody in chat, think about it. If we boost energy efficiency, somebody write into chat, I'm curious, what would happen to overall renewables if we boost energy efficiency? You've seen enough of the model now. Run your mental model. I'm going to change the overall energy efficiency, the drop in the energy intensity of GDP. Here it goes. All right, so someone in chat, answer this question. What will happen to renewables if we boost the energy efficiency of the global economy? Write it in the chat, run your mental model. Someone suggested this. Pauline says increase. Florian says decrease. So it's both. Someone said increase, right? Well, we think of them hand in hand, right? Energy efficiency and renewables. I've been saying that phrase together since I was at Rocky Mountain Institute working for Amory and Hunter Lovins in 1990. Efficiency and renewables, they work together to reduce temperature. However, like many of you are saying right here, if we have energy efficiency in buildings and industry, more efficient motors and lighting in HVAC systems, let's see, less renewables. Less renewables. Now, someone said, Sabrine, rebound effect. No, this isn't even the rebound effect. This is really simple. This is really simple. If we have more energy efficiency, overall demand for energy goes down. We don't need as much energy. This is a good thing. This is straight up good. This is what we want, to be getting more and more efficient, demanding less energy, therefore less coal, less oil, less gas, less renewables. We don't have to build as much wind and solar. That's fine. Less emissions, less temperature because we're not burning coal, oil, and gas. We don't want wind and solar for its own sake. We want it to crowd out coal, oil, and gas. That's why it helps the climate, and it reduces other PM 2.5 emissions, air quality problems. So yeah, we would have wind and solar. We get to have temperature reduction via energy efficiency down 0.3 degrees. The best way to cut emissions is to not need energy. Okay, but that said, they do work together, because watch, if we do boost renewables, we get more renewables and we get energy efficiency. The two of them go together. And the other things I showed you before, say we get storage, we get more growth, that's even better and better. So they work together for the climate, but energy efficiency would mean less growth in renewables, which is good. Okay, let's go back here. But I wanted to make sure we caught that because, and let's see if anyone else. All right, everybody, yeah, energy efficiency, etc. Okay, all the others that you came up with. Okay, here's the last one. Here is the last one I'm gonna do. I'll show you the test, and then I'm gonna ask you this question about why it happened. Okay, here is good old energy efficiency, and I'm gonna show over on the right here, methane. I'm gonna now do some things over on the right. We're gonna cut deforestation and land degradation. Temperature goes down. I'm gonna cut methane. Look at that drop in methane. We're gonna plant some trees. We're gonna have some carbon removal. Temperature goes down to 2 point, emissions go down, overall temperature goes down. We did a lot. Emissions of land use emissions. Land use, LULUCF, land use emissions from deforestation, land degradation, all of that goes down. We get down to 2.7 degrees. Renewables goes up. Renewables go up. Why? When we take action in nature-based solutions, methane and ag and food and forestry. Okay, when you answer this, if you have 2 words, hyphenate them so they're together. If you have 3 words, hyphenate those 3 words so they're together. If you see something here you like, write it exactly like this, and it'll get bigger. Why did that happen? Why did we get growth in wind and solar when we had action only in forests, agriculture, food, and land? We didn't directly intervene in the energy system, in wind and solar system, but we got more wind and solar given the assumptions in the model. The snowball effect, which is a general reinforcing loop, general interdependence, yes. Okay, interdependence. What kind of interdependence? Mindset change. We didn't model it. That could happen in the real world, but we didn't model that, so that's not it. Less methane increases overall energy demand. But why? Why did less methane increase overall energy demand? What was between methane, deforestation, etc., and energy demand? Sequestration? But why would sequestration lead to more renewables? Air conditioning. Okay, we didn't model air conditioning demand, but you would think temperature went down, there would be less air conditioning needed, right? There would be less air conditioning needed. The time lag. That's not it. Less cows. There are less cows, but why would there be more renewables? I'm still fishing for it. Someone's going to get this. Someone's going to get this. No one has written it yet. No one has written it yet. Less bioenergy. No, we didn't restrict bioenergy. We still have bioenergy. Okay, this is the toughest one of them all. This big mystery, less burning. Okay, I'm gonna have to just show you. Okay, what happened in the model? Why did this happen? We take action in nature-based solutions, etc. Temperature went down relative to what it would have been otherwise, not 3.3, but 2.7. Impacts of climate change went down. Agriculture was better. We didn't have a 19% drop in crop yield. We only had a 15% drop. Deaths from extreme heat, extreme weather events went down. Frequency of extreme heat. We had extreme heat every 22 years, not every 29 years. Less frequent extreme heat. Therefore, we had less global GDP loss. So I'm going to back it up. Here's where it was in the baseline. All the way back here. We were headed all the way at the end of the century at $167 trillion of GDP loss. Take action, less GDP loss. Less GDP loss. Less GDP loss. What does GDP do? GDP, gross world product, goods and services, is a little bit higher. See that? More GDP means overall energy consumption, the blue line, slightly higher. More energy demand, therefore more demand for electricity, therefore a little more renewables. And that demand went to renewables because renewables were so cheap. So we didn't crash the economy with climate change. Therefore, we had a little more electricity demand, and the world said, let's get it from renewables. It is the damage function, the economic damage function working in a kind of a positive way. Less damage, more economic growth, therefore more renewables. That's what's going on in that scenario. Okay, those are the 9 ways in this complex system that we could see more growth in wind and solar. All right, I want to go to the second one. The second one is going to be about overall sufficiency of the clean energy revolution. Here comes the quiz. What I'm going to do, I'm going to go in and I'm going to simulate subsidizing renewables. I'm going to boost storage so we solve that problem. I'm going to electrify everything. We have some energy efficiency. And in the land area, we're going to address land, food, ag, and methane. So it's basically, is that enough? Do you think that the clean energy revolution plus addressing food, land, forestry, methane, F-gases, nitrous oxide, is it enough to get us well below 2 degrees? Is it enough? What is the level of sufficiency of clean energy revolution? Is it enough? Run your mental models. By the way, if you have questions along the way, type it in Q&A. Do write into chat or go to the support page that's out there. Okay, what are people saying? 2.6 to 2.3 to 2.6 is getting the most votes. Almost half of you, but some people think it's enough to get all the way under 2, or maybe 2 to 2.2. but quite a range with the middle 2.3 to 2.6. Let's go try it. And note, when I do this, there's some judgment calls. This could be done more scientifically with exact numbers, but I told you I was going to encourage renewables. I was going to envision that we're going to solve some of the storage problems, challenges, we'll call them, other storage and hydrogen storage. We're also going to electrify most everything. Look at that. Brings things down. We're going to have some boost to energy efficiency. We could even imagine adding in advanced geothermal or a new source of energy. And I also said we were going to cut methane significantly and deforestation. Shoot, maybe we can plant a few more trees and have a little bit more carbon removal. There it is, though. Put it all together. Renewable energy plus the clean energy revolution. And over here in let's see, LULUC land use emissions. I just want to make sure I did enough. So land use emissions peak and fall pretty rapidly. Maybe it could fall a little bit more. Maybe we'll have, we didn't take action of food from animals. Well, yeah. Okay. I think this is enough to say that the clean energy revolution really delivered upon its promise. However, temperature is going down to 2.3 and not well below 2. You were right, 44% of you. It succeeds at transitioning away from fossil fuels. Primary energy from fossil fuels peaks and then falls steadily, but it does not phase down really. Phases down some, only to about 2000 levels, right? It doesn't phase out. And if we don't phase out, of course, we're putting so much carbon dioxide into the atmosphere from burning coal, oil, and gas still. And I'll go look. This is the energy we get from fossil fuels. We can go and look and see the emissions from fossil fuels. CO2 emissions from fossil fuels falls like that. What's that blip? You know what that blip is? That's the arrival of the new zero carbon energy after the commercialization delay. Yeah, there it is. There's a weird blip there. Okay, we have reduced those emissions, but we haven't gotten rid of them. What we're seeing is a principle that is borne out in the other simulations out there, the other integrated assessment models, which is we need to get below 2 degrees, we need to supplement the breakthroughs of the clean energy revolution with direct pressure on coal, oil, and gas. The UAE consensus said it pretty clearly about reducing subsidies. So you could capture that with some of these taxes, or this is like having reducing subsidies to the fossil fuel industry, and or, of course, carbon pricing that actually puts pressure on the industry to reduce its utilization of current capacity, but also reduce investment in new capacity. So what we just saw there is the power of these two halves of scissors. There was a really nice paper that used this analogy that seemed to capture this idea really well. Iveta Gerasimchuk had this analogy of two halves of scissors, discouraging fossil fuels or encouraging less, and then secondly, encouraging clean energy as two halves of scissors that cut greenhouse gas emissions. It's a nice analogy for this idea. And I just want to note, it works the other way. I could have done the test the same way. Like, what if all we did was did the land-based forests and food, and then tax coal, oil and gas and or things like carbon pricing that reduces things alone isn't enough. What we need to do is also have breakthroughs in clean energy and electrification and renewables, et cetera, to get below 2 degrees. We need both sides. So when you think of this, I'm curious of that second side of pressure on the fossil fuel industry. When you think of that, what comes to mind about how to do it? Please go to the poll and vote. Please go to the poll. What do you think are the highest priority policies? Carbon pricing, banning exploration and drilling, reducing subsidies. People are voting for that. Others that I'm offering here, building codes like gas in buildings, or cutting gas installation into buildings like Washington State has under the leadership of Jay Inslee, setting dates to ban internal combustion engines, countering fossil fuel infrastructure locally, divestment in finances from oil and gas companies, international treaties, or addressing pipelines. There are your votes. Okay, these are some of the ways that we can complement the clean energy revolution with pressure directly on fossil fuels. So I just want to summarize what I just said there. The role of the clean energy revolution and the contribution of clean energy to avoided emissions is huge. When we added in all the land-based work, we got all the way down, 2.3 degrees. And yet, even when we add in those successes, it's not enough. Using the scissors analogy, cutting the emissions necessary for 2 degrees would also require discouraging fossil fuels. And you just saw some of the ways to do it. That's the summary of this second surprise. I want to also just make sure I'm summarizing for you the others. The first one that I hit, I want to make sure you saw where we landed. Back to the wind and solar story. The 9 ways, more subsidies, boosting long-term storage, discouraging oil, discouraging coal, gas, carbon price, electrification, nature-based solutions, and deforestation and food also did it. But we saw energy efficiency actually did lead to more growth, but we should do it. It's really important. It's an important ally, but it won't boost the growth. Some other things as well. Okay. All right, so we've gotten through 3. I'm going back. I'm going to think about the next one was really about removals. When you think of carbon removals, we've had a surprise, some of the surprises when some of the recent modeling we've done about carbon removal. So what are the most discussed ways to boost carbon removal? When people say, oh, we're going to do carbon dioxide removal, CDR, negative emissions, what gets discussed? If you have a word, something that has 2 words, hyphenate it. If you have 3 words, hyphenate it as well. If you see something you like right here, like sequestration, direct air capture, write it again and it'll get bigger. Trees, fantasy, recycling. Recycling doesn't lead to CDR, carbon removal. Someone said it's a fantasy. Natural sinks, carbon capture technology, sequestration. CCS is carbon capture and storage, crushed rock or mineralization. DAX is direct air capture with CCS. DAX, biochar, where we grow trees and use this chemical process to turn it into a kind of a charcoal, spread it on land. Natural sequestration, seaweed ocean sink, bamboo. So many ideas here. Thank you. This is great. This is what we do hear about. I'm going to go and pull up the model again and look at this area of carbon removal, particularly on land. If you go down here to carbon removal, and now maybe I'll just, oh, I'm going to just do it. I'm just going to take a minute. Why this is so important to talk about. I'm just going to come back to the good old bathtub. This is one of the first ideas that brought me into this work. John Sturm and Linda Booth Sweeney wrote this paper in like 2003 or something, framing it this way. Here is the carbon challenge, everybody. CO2 in the atmosphere is the stuff that is insulating the world and trapping heat. That is like the water in the bathtub. Emissions, burning coal, oil, gas, deforestation emissions, etc., going in to the bathtub. Net removals is what's going out into biomass, most of it into oceans. What we control is going into biomass or into other storage. Shove it underground. Right now, where do we sit with this bathtub? We have a bathtub with double going in than going out, like 4 and 2, double going in than going out. If that's the case, double in going out, what am I talking about? Here it is, double in going out. The red line going in, CO2 emissions, blue, net removals going out. We have a bathtub, which is CO2 concentration on the right, double going in what's going out. Therefore, of course, concentration is going up. Of course, every year we hear the news from Mauna Loa that CO2 in the atmosphere is a little higher. Here we are, 417 parts per million, headed towards 627. Why? More is going in than is going out. So the conversation here is, can we control not just what's going in, and of course, all these things we do, reduce those emissions. There are other feedback effects, but we can also boost the removals. Various carbon removal, can we boost it as the second way to address this? So I'm going to now pull up under carbon removals, CO2 removals from land. And I'm going to focus in this area on land, forestry, and food, deforestation. Okay, let's think about this for a second. Here we are. These are the removals from land. How much CO2 is getting pulled out of the atmosphere and being sequestered? Notice when we cut deforestation. Now, one big thing about cutting deforestation, it's great. You don't burn trees. We don't have carbon going into the atmosphere and being released from soils. Emissions go down, but also look at what happens to CO2 removals from land. This is carbon dioxide removal into natural sinks that doesn't require more of anything. We're not doing more. We're just not chopping down all of these trees that are working so hard. They're not working hard at all. It's photosynthesis. They're using their chlorophyll to pull carbon out of the atmosphere into the biomass and then into the soils. So this is natural carbon dioxide removal by reducing deforestation and land degradation. I'm going to do it again, but this time with more actions. I just said reduce deforestation here. We also can reduce land degradation, and that will boost the removals. Also, diets, food from animals, and food waste in the food system, boosting removals. Changing diets and improving agriculture is carbon dioxide removal, boosting CO2 removals from land. Were there others that I wanted to change here? I think those are the big four. Now, of course, if we plant some trees, these are other things that do it, but we are limited by how much land we can do that on without threatening equity, pushing people off their land. There isn't that much land we could do. We could plant more trees, although we should do it for many other reasons other than the climate. But these are some of the areas that give us natural carbon dioxide removal. And I was surprised by how much we get. Now, of course, there are other things that we can do, and you can go test those at En-ROADS, but those are the ones that you wrote about. Direct air capture, where there's some potential for that. And you mentioned ag soil carbon and biochar, and oh, wait, that was the start year. And other things like this. Carbon capture and storage were also improving in the model right now. Okay, what's my big point over here? My big point over here is protecting forests and reforming food and agriculture are less discussed, but accessible approaches to carbon removal. Many policies related to forest and agriculture could boost CO2, changing diets, cutting food waste, protecting land from deforestation, reducing degradation, all increase the amount of land with older trees, increasing sequestration and CO2 removal. Okay, last one. Here comes the last one. Carbon dioxide, carbon pricing. I'm going to put up over here, carbon price. And over here is going to be overall carbon not the carbon intensity. I want the energy intensity, energy efficiency. Over on the right is the energy intensity of GDP. How much energy does it take to bring $1 trillion of goods and services? As it goes down more, that means more energy efficiency. What is going to happen to energy efficiency if I boost carbon price? Right into what is going, someone write into chat, what happens to energy intensity and energy efficiency if we boost carbon price? Write it in there. Goes down. Efficiency goes up. Energy intensity goes down. Let's go try it. I was surprised how much this is the case. Watch this. By setting a carbon price, we have the energy intensity drop faster. More energy efficiency. It takes less and less energy to deliver goods and services. Why? Energy is a little more expensive. More expensive energy means an incentive for energy efficiency and consumption going down, more energy conservation. Now, this creates equity problems. We got to make sure people can pay their energy bills, but this is an interesting side effect of these energy prices. As Eduardo says, people buy appliances that use less energy. Exactly. Okay. I said this was the last one. Well, let me give you the summary. The summary of that one is right here. Carbon pricing boosts the cost of energy, creating incentives for energy efficiency, investment, and conservation by all sectors, decreasing the energy intensity of the global economy and reducing emissions. This complements the benefits from encouraging low carbon energy and discouraging fossil fuels. Got to be careful of the equity challenge, however. Okay, the last one. I said it was the last one before. I was wrong. Let's talk about what is possible today. Right here, click to the right or the left of the dot. What shall we do? What do you feel is possible for us to implement in the world? Click on this diagram. What is possible to implement in the world? Less coal, more renewables, more carbon pricing, more electrification, more energy efficiency, less methane. Click away. You're doing great. Yes. Electrification, less deforestation, less methane, zero carbon energy. Yes. What is possible? All of these things. Oh, I love saying this. We're creating our vision of what we'd like to see in the world. We're creating, there's a video that we put in the Mastering En-ROADS course, our vision, the top end of this rubber band. Our vision is here, our current reality. You are right now capturing the vision of what we'd really like to see in the world. And one note, if you want to do this, ask the same question of your colleagues, your community, your bosses, the board of your organization, anybody, you should go take this simulator and run a workshop with them, show it to them, have them create their vision of what we could do. If you'd like to bring us in online or in person, we run 1 hour interactive group exercises virtually. We call it the Climate Solutions Workshop, 2 to 3 hour interactive role play exercises, the climate action simulation game, or we customize experiences over here. Catherine Markova, who's on the call, would be thrilled to get an email from you saying, here's what we really want to do. We can do it ourselves. We have 780 En-ROADS Climate Ambassadors. If you're an En-ROADS Climate Ambassador, write into chat right now and say, that's me. I am one of those people who went through the 8 hours of training. You can do it yourself as well. These are some of the people who have hosted these workshops: Andrew Greenspan at HSBC, Roberta Barbieri at PepsiCo, Erin Felter at Okta. Blown away, she said. Here's where to find Catherine: solutions at climateinteractive.org. Okay. Oh, and by the way, if you want to do it yourself, you can go study how to do it and be like these people who shared their pictures. These folks played the game version. It's very silly at times if you want it to be, and fun. In Australia, Crystal Noiser in Washington, D.C., Hofstra University, Krista Farmer did the game version. This is a group in Peru, in Ghana, in Temple University. They played the game. Victor Joza and Ava, who's on the call right now. South by Southwest, Ellie and Ben Wolkin, Jose in Peru, in Canada. You get the idea. You can go engage people in Ireland by taking this course. Please go post the link somewhere in chat, would you, Ava? But I'm jumping ahead. Here's where we were. This is what you said you wanted to see. So what is possible, everybody? What remains possible today? Well, with renewables and pressure on coal and oil and gas, with carbon pricing and energy efficiency and electrifying everything and cutting deforestation and land degradation and planting some trees and investing in some CDR, cutting methane, etc., we can get well below 2 degrees. And if we imagine some levels of new technologies and carbon removal beyond that, well beyond what we know how to do today, perhaps are even ways to get to 1.5. The point is, it is still possible to bend this curve down towards zero in order to get to where we need to do. What we know what we need to do. We need to phase out burning of fossil fuels, need to cut methane, and we need to protect forests. It remains possible. How do we get there? There's no one thing. It takes many seeds to plant this garden. It takes many seeds to plant the garden. Along the way, there are some surprises. So many ways in this tightly coupled system to boost wind and solar. So many interesting ways to increase carbon removal without having to build any machines, but just with natural methods to do it. Clean energy alone isn't enough to get us there. We need to have both halves of the scissors: pressure on fossil fuels and the clean energy revolution. Along the way, carbon pricing also boosts energy efficiency. These are some of the surprises that we discovered that we hope are interesting and useful to you. And just to make sure that that last insight landed very clearly, there it is. It is still possible to enact policies and investments that would reduce the burning of coal, oil, and gas, cut emissions of methane, nitrous oxide, F gases, protect forests, enough to limit warming. It takes many seeds to plant the garden. It's not going to be easy, my friends. It's going to be worth it. All right, that's our hour. That's our webinar. We are going to stick around and answer your questions. So if you have more questions, please write them in Q&A. We're going to take them live, but mostly take this simulator, show it to people, engage others. And if you create value in the world, send some of that value back to En-ROADS. We are a public institution funded by donors around the world. Send us a note here if you'd like us to come run a workshop for you, or if you happen to know a family office, a foundation, or somebody who wants to deliver significant climate results. That's what we do as a not-for-profit climate tech organization. All right, bye-bye, everybody.